Hello and welcome to a digital lecture for Sully Community College. This lecture will cover section 6.2 for Intro to Statistics, considering line fitting, residuals, and correlations. Here, we are going to assess the relationship between two quantitative variables using linear regression, which is a very powerful statistical technique where a straight line is overlaid on a scatter plot. The two variables in a scatter plot, x and y, are known as the explanatory and response variable respectively. Remember that the explanatory is used to try to predict the response variable. Also, keep in mind that we will be working specifically with linear regression, which means that we will only be able to analyze and detect linear trends. So we can only consider models that are based on straight lines in this book. If data show a nonlinear trend, more advanced techniques should be used. So these advanced techniques do exist, but we will not be using them in this course. When we create a straight line to try to fit data in a linear regression, we will oftentimes be interested in how well it fits the data. To really determine what that means, we look for residuals on individual values, which is the distance between the prediction line and the actual observed data point. Specifically, it is the vertical distance, which represents the response variable y. In this note here, we have the residual of an observation x, y is the difference of the observed response y and the response we would predict based on the model fit y hat. So the residual here, for example, could be the observed value y minus the value we would get from our model y hat. Keep in mind that what we mean by the model, we're referring to the equation for the straight line that we are trying to fit. Y hat equals b sub 0 or beta sub 0 plus beta sub 1 times x. We identify y hat by plugging x into this model. If we just want to look at the residuals, we can make what is called a residual plot, which only graphs the residuals themselves. If a residual is above the x-axis in a residual plot, then the observed value is higher than the predicted value in the scatter plot. The same is true for the negative values seen in a residual plot. The correlation coefficient will also be an important tool for us to evaluate the linear relationship. The correlation coefficient R describes the strength and the direction of the linear relationship between the two quantitative variables. Pay very close attention to the fact that it's finding both the strength and direction, but specifically for a linear relationship. This value R, the correlation coefficient, will not be useful for any other kind of relationship. So, if R is not very good, as we'll show later, if R is a bad value, that does not mean that there is no relationship. It means that there is no linear relationship. So keep in mind that we're always talking about linear relationships here. It always also takes a value between -1 and +1. That means that R is between -1 and +1, so -1 is less than or equal to R is less than or equal to 1. Some specific characteristics of R, some that have been discussed, some that have not. The sign of the correlation coefficient shows the direction of the linear relationship. If there is a downward trend, which means that I have values in the scatter plot that are both in the top left corner and the bottom right, then that means R is negative. If it is the opposite, I have a lot of values in the bottom left and the top right, then that means the upward trend R, it would be a positive value. Only when the relationship is perfectly linear, though, will we ever see a correlation coefficient that is either exactly -1 or +1. If the relationship is strong and positive, though, the correlation will be near +1. And if it is strong and negative, it will be near -1. Not exactly, but closer. If there is no linear relationship, then that means the correlation coefficient R will be near 0. So, if R is close to -1 or +1, it implies a linear relationship, either a positive or -1. But if R is closer to 0 than it is to 1 or -1, then that implies that there is no apparent linear relationship. Note again that linear is bolded and underlined here. R is only useful for linear relationships. Let's look at an example on the next page. Here we have 5 different graphs, and we're going to approximate R. Now, given what we have here, we're not really going to calculate R specifically. We're just going to make up a value that seems to fit this relatively nicely. For some of these, they're going to be pretty easy to make. For example, if I'll look at the second and fourth example, so this one and this one, I see that for these, both of these look almost like straight lines. I maybe see a little bit of a deviation on 1 or 2 of these points, but very little. Since these look near perfect to straight lines, I'm going to say that their correlation coefficients are likewise either exactly 1 or -1. Since the second example, I see a positive trend, values in the bottom left and the top right, I'm going to say that this has R value of about +1. Whereas the fourth example has a lot of values in the top left and the bottom right, so this likely has a correlation coefficient closer to -1. Aside from that, the rest of these start to deviate away from being a perfect linear relationship. More egregiously, the first example, I see a scatter plot that is true to its name. I have points here that are scattered everywhere, and I do not see anything that could represent a linear trend. There's no way that I can draw a line that I really think fits this data in any particular way. So I'm going to say this R value is pretty close to 0. The other ones are a little bit harder though. If you look at the third example, this has a positive trend, similar to the second one. I see values in the bottom left up to the top right, and if I were to draw a line in between those, it does seem like that fits the data pretty well, but not perfectly. I do have values, the observed values, that have positive and negative residuals. So I'm not going to say that R is perfect to 1 or -1. However, because this looks like a positive trend, I'm going to say that it's closer to +1 than it is to 0. So I'm going to estimate something like positive 0.7. For the last example, this just looks like the third example, but flipped so it has a negative relationship. Still, I see that if I were to draw some sort of a line that represents this data, it's not going to fit perfectly, so I don't think it's a perfect -1 for the correlation coefficient. I think it's something that's deviating away from that. So I'm going to estimate something, I'll just say -0.7. Keep in mind again that I was just estimating here. If you looked at one of these, specifically 3 or 5, and you were thinking that maybe this should be something like 0.75 or 0.6 or something like that, that's fine. As long as you're seeing the fact that there's a stronger linear relationship than there is a nonlinear relationship. If you have any further questions, be sure to review the example videos or ask your instructor.